Like if we notice that every time a storm is coming, the crickets seem to start singing, we can try to prove that these variables are correlated through statistics. Statistics can offer us insight into patterns and trends within the world. It's a way of understanding the world around us. By understanding statistical concepts, we can gain a deeper appreciation for the interconnectedness of all things. So, we might have a bunch of variables that we notice, like the number of crickets outside, whether or not a storm is coming, what time of day it is, whether we're in the city or the country, if there are animals nearby, what parts of the world we're in, what season we're in, etc. This is a lot of information to account for, so it might be easier if we simply picked a few variables to look at rather than every variable available. Since we can't look at the entire world, we might want to take some sample measurements to make some educated guesses about the whole phenomenon that we're looking at. Some variables might be measured in numbers, whereas other variables might be measured in categories. In statistics, we collect data, then we organize and analyze it. Once we look at all the data we've collected, we have a bunch of numbers or a bunch of categories, and we need to make sense of what we're looking at. What does all the data we've collected mean? So, first, we need to decide what we want to measure. The thing we are measuring is called our variable. Then we have to collect data that will hopefully tell us more about the variable. For instance, if we are measuring average test score for a school, we would collect data on test scores. Our variable, the thing we are measuring, is average test scores. So, we go collect the data, which are test scores, to measure this. If we were to collect data on every single test score, then we would call this population data because it covers every test score in the population. However, that would take a very long time, or something where every single individual is accounted for. We call population data a parameter. You can remember this because parameter and population both start with a P. Normally, getting population data takes too much time and resources, and we can be a little lazy in statistics, so we might rather just get a sample data, which we call a statistic. Both statistic and sample start with an S, so you can remember it that way. A sample is a portion of individuals that are in the full population. So, a parameter is from a population. A statistic is from a sample. Normally, we are looking at sample data, which is a statistic. But there are ways to estimate population data from statistics, which come from sample data, which we will get into. But for now, we are hoping that measuring the sample will give us similar data to if we actually did measure the population, or if we had every person accounted for. An example might be if you saw a population of ducks, but you have a sample of 10 ducks from that population to work with. The 10 ducks would be your sample. Or another example is maybe you want to make a guess on the population on the proportion of women that go to a school, but you don't want to count every single person at the school to figure it out. So instead, you sample one classroom. You would hope the statistics from that one sample or that one classroom are similar or representative of the entire school, which would be your full population. You would not get the exact same proportion of women in one classroom compared to the entire school, but maybe this could help you get a rough idea. There's always going to be a difference between your sample data and your population data because you aren't accounting for every person. This is expected. We call this difference sampling error. Sampling error is okay. It is expected. That way we have reflect the whole school very well. So we need to think of better ways of getting samples. Luckily, there's different ways we can get samples. We really want all of our samples to be random, which means each sample has an equally likely chance of being selected. To get random samples, we could use a dice, or we could use an appendix, which is just rows of random numbers, or we could use technology like a random number generator. Even if we randomly pick samples, we might have unintentional bias, so it's better to just use technology or dice or something like that to pick for us. So, with the first example I gave, with the classroom being our sample data, this might not be the best way to measure how many women are at the school, because we are not only looking at one classroom. So let's look at some ways around this. One method is called stratified sampling, where we divide the population into strata. Then we randomly sample from each category. A strata is a group, so we divide the population up into groups called strata. Then we use our either technology, appendix, or dice to take samples from each strata. So, with the example of measuring the amount of women at a school, we would consider the classrooms our strata. In this example, let's pretend each classroom has the same number of people to make it simple. This is not always the case, but we'll just say that our classrooms have 30 students each. So we have a list of all our classrooms, which are our strata. Then we randomly select a few students from each classroom. Maybe we assign each person a number, and then a random number generator calls 5 numbers. We would have 5 students from each classroom be our sample. This method can help us estimate the diversity in the population based on our sample. Another way to find a random sample is to use systematic sampling. In systematic sampling, we want to look at every kth person, which is every K person, the letter K. K represents a number. So maybe check every 10th item to make sure it's not damaged or anything, rather than checking every single item. Maybe you could remember this by thinking of systematic sampling as a system or a factory that's checking every 10th croissant for mold. It's a systematic approach. You also don't have to start at the very beginning of the list. You could randomly start at any point in the list. So maybe you start with the 22nd item and go down the list after that, accounting for every 5th item or whatever random number that was generated for you. Or maybe you only look at the last 1,000 items. This would be good if you have thousands or millions of data points in the full population, and you don't need such a giant sample size because you're trying to find the 5th item out of 1 billion data points. That would take forever. So you would just need to make sure this method is appropriate for what you are measuring. That's why there's different approaches to collect random samples. So, systematic is ordered, and then we account for every k number, and k represents a random number. And stratified is when we break the full population into groups called strata, then take random samples from the strata. Next, we have cluster sampling, which is kind of similar to stratified sampling because both divide the population up into groups. However, instead of taking random samples from each group, we just randomly selected a few groups to look at everyone in those random groups. So, cluster sampling. An example of this is we want to determine how many women go to a school. Our different groups are the classrooms. Maybe there's 20 classrooms in total. We are going to pick 4 classrooms randomly and account for every person in those classrooms. That's just an example, though. You could pick a different number of classrooms if you wanted to. But in this example, we picked 4 classrooms. So our random generator says that we pick classrooms number 3, 5, 13, and 19. We would survey every single person in those 4 classrooms. So that is cluster sampling. Cluster sampling is different from stratified sampling because we pick random individuals from each strata. But in cluster sampling, we pick random groups and account for all the individuals. But we only look at certain groups according to our number generator. If you are using a combination of sampling methods, we call this multistage sampling. If it seems very complicated and could have way more women or way less women in our sample. That doesn't represent the actual population very well. Or maybe we are looking at the proportion of extroverts and introverts, and we only survey people who seem approachable. Obviously, in this example, that would mess up our data. So that's why we don't really like to use convenience samples unless collecting a random sample is not an option. So, there's always room for improvement in your samples. They are never going to 100% represent the entire population. That's just a way to make estimates about the full population. There's going to be a little bit of error, which is totally fine. Like we said, that's called sampling error. It's the difference between our sample data and the population data. If you want to learn more about statistics, I will be uploading topics on qualitative and quantitative data and breaking it down more slowly in the next video. If you have any suggestions or requests on different topics or anything like that, please make a comment. But otherwise, I hope you are de-stressed and trust in your knowledge.